In this video, we are going to look at different ways to represent precipitation reactions. So the solubility rules that we learned about in the previous video also helped us to predict which chemicals are going to form precipitates or solids when reacted. These types of reactions are called precipitation reactions, or as we've seen before, they are double displacement reactions. And so we can represent these reactions in three ways. We've seen balanced chemical equations already, but we can also represent them as total ionic equations and net ionic equations. So these are going to be new for us in this video. Let's start with a balanced chemical equation then. So this equation shows all of the ions present in the reaction container. So this is going to be your typical double displacement reaction. We've got lead nitrate reacting with potassium iodide. So that's going to produce lead 2 iodide, and it's going to produce potassium nitrate. So we want to use our solubility rules to predict if either of these are insoluble or not. So we know from our solubility rules that lead iodide is insoluble. So it is going to form a precipitate with this reaction, whereas our potassium nitrate is soluble. So it's going to remain aqueous. Okay, and as with any balanced chemical equation, we want to make sure that it's actually balanced. So to do this, we need 2 in front of the potassium nitrate, and then we need a 2 in front of the potassium iodide. Now, if we want to take this one step further and show the total ionic equation, what this does is it shows all the ions present in the reaction container, but dissociates or splits up anything that is aqueous. It is really important to remember that solids do not dissociate, so they stay together. So if we're taking our last example, for example, lead 2 nitrate is going to dissociate into lead 2 plus ions and nitrate ions. And since our formula was Pb bracket NO3 bracket 2, we would have 2 nitrate ions. Okay, so same with potassium iodide. It's going to split up into its ions, and since we had a 2 in front of it, we'd have 2 potassium ions and 2 iodide ions. And then that's going to react to produce lead 2 iodide. Now, because lead 2 iodide is our precipitate, we do not dissociate it. We keep it as one compound. And then we also have potassium nitrate, which is soluble, so that is going to dissociate into 2 potassium ions and 2 nitrate ions. So you got to make sure you've got charges for everything, that you're balanced, that your solid stays as one, and that you put in the states. Okay, so anything that's dissociated into ions is aqueous. Anything that's a precipitate is a solid. Now our net ionic equation is going to take our total ionic equation and show the ions that form the precipitate. So all other ions in the equation are considered to be spectator ions because they do not participate directly in the reaction, and they remain dissolved as both reactants and products. So that means in our reaction that we saw before, what you want to look for are ions that remain the same as both a reactant and a product. So in the previous example, we have 2 potassium ions on the reactant side, and we've got 2 potassium ions on the product side. So we would say that the potassium is a spectator ion. The same happens with the nitrate ions, is that we have 2 on the reactant side and 2 on the product side. So those are spectator ions as well. But when you take a look at the lead 2 plus and the 2I minus ions, they don't appear as ions on the other side. And in fact, what's happening is they are combining together to form our precipitate. So this would be our net ionic equation showing just those ions that are forming the precipitate. Now, just to go through two more examples, what we want to do is if a reaction occurs, which means that a precipitate must form in order for a reaction to occur, we're going to write the balanced chemical equation, the total ionic, and the net ionic equations. If no precipitate is formed, no chemical reaction actually occurs, and so we're just going to write no reaction. So for this first one here, sodium chloride and calcium bromide, you would expect the products of sodium bromide and calcium chloride. Now, if you take a look at your solubility rules, both of these are soluble. And so what that means is that this double displacement reaction wouldn't actually occur. So you would have no reaction. And that's because you would have all spectator ions on both sides of our equation. For our second example, what we're going to do is our double displacement. So let's start with that. We're going to get a lead 2 carbonate and a sodium nitrate. And so we know all nitrates are soluble. But if we take a look at our lead 2 carbonate, this one's going to form a precipitate. So this reaction will occur, and we need to balance it with a 2 in front of our sodium nitrate. So to write our total ionic equation, we're going to split everything up into its ions. So we got Pb2 plus, and we got 2 nitrate ions, and we got 2 sodium ions, and a carbonate ion. I know this is a little tedious, but we'll get through it. So our lead carbonate is our precipitate, so we don't dissociate that one, but we do dissociate our sodium nitrate. Okay. All right, so that is our total ionic equation. So to get our net ionic equation, we're going to find our spectator ions. So if you take a look, nitrates are on both sides, sodiums are on both sides, so those are spectator ions, meaning that our net ionic equation is just going to be Pb2 plus our carbonate ion to produce our precipitate of lead 2 carbonate.